Okay, so we've been talking about alkenes and their polymerization, and now we'll go on to the triple bond analogs, acetylenes, for just a little bit, and then on to conjugated systems, starting with allylic intermediates and then dienes, and then in general about linear and cyclic conjugation and aromaticity. So we can generalize from what we know about alkenes to acetylenes. We have the same kinds of reactions, additions of HBr, addition of water, addition of H2, but all these have a little bit of a different twist. HBr, we already mentioned this, but I'll go over it again, stepwise addition, but Markovnikov. The addition of water, we see the possibility of keto-enol tautomerism and regioselection, as in alkenes. And then in H2, there's a question of a stepwise addition, one double bond and then the other, one multiple bond and then the other, and the question of stereoselection. And finally, some stuff about acidity and base catalyzed isomerization of acetylenes, which you'll see are much more acidic than alkenes are. Okay, first, we talked about this already, but just to go over it quickly once again. It's possible to add HBr to a triple bond, like 1-hexyne, and you can use a catalyst that helps make the HBr more acidic, and you can get a single addition to give a hexene, 2-bromo-1-hexene. And you often use an inhibitor so that you don't get free radical addition of HBr. Now, we mentioned before it was 100 to 1,000 times slower than the comparable ionic addition to the alkene. And the reason is the vinyl cation is not so great an intermediate. And you can see that already in gas phase ionization of the chlorides. The one that gives the ethyl cation requires only 193 kilocalories per mole to ionize the chloride. But the vinyl compound, to make the vinyl cation, requires another 32 kilocalories per mole. It's hard to make the vinyl cation. So that's what, of course, you make when you add the proton to the hexyne. And it's possible to isolate that in 40% yield, which seems funny, as we mentioned before, because if it's not very reactive, wouldn't the hexene you make be even more reactive, so that it would be impossible to isolate something that was part way along? And so you can go further to 2,2-dibromohexane. Obviously, it's slower. And it gives a second Markovnikov addition, right? Which, if the bromo substituent slows the addition to an alkene in order to make it slower than the initial addition to the already slow alkyne, why is the orientation Markovnikov? And we saw the resolution of that riddle a few lectures ago, that the halogens do two things. They withdraw electrons through the sigma bond and therefore make it harder to form the cation. But if you form the cation, make it next to the halogen so that at least you can profit from stabilizing the unshared pair on the halogen. Okay, we saw that before. Now, hydration and hydrogenation of alkynes. First, hydration. We can do the same kind of thing we did before the alkoxymercuration, which you may remember forms an unsymmetrical bridged ion. Then water can open it up, and you get the addition of mercury and OH, hydroxymercuration. Now, remember what we did before when this was an alkene to begin with and we had a single bond in the product? Nobody wants the mercury compound. What do you do? Why did people make it? The next step was reduction. Remove the mercury and replace it with H, so that what you added was effectively water, right? So they used sodium borohydride to do that. However, it doesn't wait around for you to do that under these conditions because you have acid there. And with the double bond, it's possible for the acid to add to it. Now, so you get that cation. What's good about that cation? Why is that easier to form than it would have been if it had just been a regular alkene? Elisa?
There's the O there that's taken.
What does the O have to do with it?
It's able to deprotonate and then form a double bond.
No. well, a double bond gets formed ultimately, but what's good about the cation when you have the oxygen next door? Brandon, what do you say? Yeah, it has unshared electrons in the p orbitals that can be stabilized by the vacant p orbital next door, so that there's a resonance structure that makes it unusually stable, a HOMO-LUMO interaction. But what leaves then is the mercury plus, okay? So you get this compound, which is an enol. Notice that it was formed with Markovnikov orientation, as it would have been the case if it had started with an alkene, right? But enols can undergo this same acid-catalyzed reaction to get that cation, which is stable, as we can see in that resonance structure. And what could that do? Lose a proton, okay? So it gives a ketone. This got traditionally the name keto-enol tautomerism. Tauto means equivalent to, right? So the idea was that the ketone and enol interconverted so easily that it was impossible to isolate one or the other. So that's a really easy allylic rearrangement from one end of from one allylic position to the other. Okay, and we talked about the keto-enol equilibrium last semester when we were talking about bond strengths. Just to remind you, this is where we went through it, added up the bonds, and showed that the ketone is much more stable than the enol. I'll just flip through that. That's just so when you're reviewing it, you can look at it there. Okay, so it goes to the ketone. So the product from hydration of an alkyne is a ketone. Okay, the alkoxymercuration of an alkyne. It doesn't wait around to do the sodium borohydride reduction. Now, remember, you could do the other thing in an alkene, add in the other regiochemistry by using a borane. For acetylenes, you use a special borane, which has you get a vinyl borane as the product, and it won't add a second time if you have those R prime groups sufficiently hindered so that it blocks access. Okay, a way you can do that is with a compound called diacetyl borane, which is made with BH3 and that alkene. So you might think about what the R groups are, the R prime groups that you put on there to make that hindered one with a single H that N adds only once. So you get that vinyl borane. And remember what you did with boranes when we were added to a double bond? What was the next thing? Hydroboration, and then what? Incidentally, this reminds me that a week from today we have another exam, right? And it'll cover today's and Wednesday's lectures. I'll give a review session Wednesday evening. I'll tell you, probably 8 to 10. So you have a week to learn this stuff. Okay? It's good news, okay? Anyhow, it was hydroboration, oxidation was the next thing. Remember, you treated it with hydrogen peroxide and alkoxide to make the borane into an alcohol, right? And then, in this case, we have an enol as above. So that'll isomerize to a carbonyl compound. But notice it was anti-Markovnikov. The addition above was Markovnikov. The oxygen went to the more substituted center. This one, the trick you use when you do borane, the O goes to the less substituted center. So in that case, you get an aldehyde. So the H2 on one carbon and the O on the other add in one sense here and in the opposite sense here. So that's nice because if you're a synthetic chemist, that gives you the control of which product you want to get. You can use one method to get the Markovnikov ketone and the other to get the anti-Markovnikov aldehyde. So this is hydration with either regiospecificity. But also we could talk about hydrogenation, adding H2, and here it's a question of stereospecificity. Up at the top there, if we take an alkyne and reduce it with H2 and a catalyst, as we talked about with an alkene, you can get first this alkene. And you use a special catalyst. This was developed by a guy named Lindlar, and he added lead to the palladium catalyst. Lead is a poison for catalysts. It makes the catalyst less active. Why might you want the catalyst not to be very active? Chris? So it doesn't go all the way. It'll do the acetylene, but it won't do the alkene, so you can stop and get it there. If you use a more reactive catalyst, you can go all the way. Okay? So that deactivates the palladium and stops at the alkene stage. And notice the two hydrogens came in from the same side. So it's a syn addition. For example, you get a 97% of that syn addition if the R is this CH2 taken 3 times ester group. Okay? Now, on the other hand, if you use sodium and ammonia, a thing called a dissolving metal reduction, you get the opposite stereo specificity. It's an anti-addition, right? Now, it might wonder, the syn addition we talked about before, the same thing in an alkene about how the palladium comes in an attack, then it gets replaced by one hydrogen and by another hydrogen, always front side attack, so that it comes out to be syn. That one won't surprise you. But why does this one give anti? The key is that it's a dissolving metal reduction. Incidentally, in that case with N-propyl groups, it's an 80 to 90% yield of that anti-addition, and I think none of the syn. Okay, so it's a dissolving metal reduction. So sodium actually dissolves in ammonia to give electrons and sodium plus. So it's a very interesting ion pair. It's an electron and sodium ion. Of course, the electron is solvated by ammonias around and about it. And it looks blue, the solutions of electrons. Okay? Now, if you have an acetylene, an electron will add to it. What orbital will it go into? What's the LUMO going to be? Yeet, what do you say?
Carbon, pi star.
Yeah, pi star. So notice it puts in, there already is a pair of electrons in that corresponding pi orbital. So now you have 3 electrons among those 2 p orbitals. So you can write it as one being an anion with 2 electrons and the other being a radical with the 3rd electron. Okay, so we have an anion radical as an intermediate. That, of course, is a very strong base, the carbon anion. So it can react with the ammonia and pull off a proton, right? So we've added an electron and a proton. That's the equivalent of adding a hydrogen atom, although it's done as 2 stages, okay? So we get this vinyl radical, which is bent, right? They're sp squared hybridized at that functional carbon, but they invert easily in the case of a radical, right? So it goes back and forth between the R being on the same side and the opposite side. Now, which one do you think is favored? Obviously the one with the R groups on the opposite side. So at equilibrium, that's the one you have. And now a second electron comes along and goes into that singly occupied orbital. So now you're going to have a pair of electrons there. We'll write the minus charge in that sp squared hybridized orbital. But now it's harder to invert. Remember XH3, how if you added more electrons, it ceased to be planar and became pyramidal. The same idea here. So now it doesn't flip back and forth rapidly. So a second proton can be taken away from the ammonia, and we get that product. And the 2 H's are on opposite sides. It's an anti-addition. Why anti? It's because that isomerization of the radicals favored the one with the R's far apart from one another. Then it got trapped as the anion in that geometry, and then it went on to give the anti-product, as we gave yields of on the previous slide. Now, the final special thing about alkynes that we're going to talk about is their acidity and how that relates to isomerization of alkynes. So we looked before at these pKa values for carbon, nitrogen, oxygen, in the order you would expect them to be. But that if you have an sp squared hybridized carbon or an sp hybridized carbon, they get much more acidic. Okay. We talked about this before. And in some cases, if you have next door, if you're breaking a CH bond and next door there's a double bond, you can get extra acidity, okay, that stabilization. Okay, so anyhow, we looked at those pKa's, and here we can see the energies of these three isomers of an alkyne. So you have the alkyne on the left, the lowest energy is heavily substituted. On the far right is one that it's the end of the chain, so not having as many carbon-carbon bonds with the special sp hybrid, it's not as stable. And in the middle we have the diene version, the 1,2 diene. So at equilibrium you would strongly favor the internal acetylene, but how do you establish an equilibrium among these? You have to move hydrogens around. So at equilibrium, given those energies, there's only 0.1% of the 1,2 diene and 0.03% of the terminal acetylene, so very little of those. Okay, so we just talked about the fact that the terminal acetylene could be, or the internal acetylene could be acidic because of the pi bonds next door, making the anion more stable. So indeed, you could do that, or you could do this one. That was on the previous slide as well. Or you could do the terminal acetylene, which is the easiest one to take off, to put the electrons in the low energy sp hybrid orbital. Now, the pKa over here is 38. So that means that the Ka is 10 to the minus 38, right? Or the energy involved in getting up there is about 51 kilocalories per mole. Okay, over on the right, it's 33 kilocalories per mole. Still way uphill, right? So those energies are quite far above we know this, that's what we know from the pKa's. So if we wanted to take off a proton, then put it back on, then take off a different one, put it back on, and finally go to the final anion, we'd have to go way up in energy. If you have to go up 51 kilocalories per mole, that's not a very fast process. The rate constant for that would be 10 to the 13th per second times 10 to the minus 38, or the half time would be about 10 to the 17 years, which is about 10 to the 4th times the time that's elapsed since the Big Bang, so don't wait around for that one to happen, okay? So obviously you're not going to be able to isomerize that way by just letting it ionize off a proton. But if you put hydroxide in, it reacts with the proton to make water, and that's worth 21 kilocalories per mole. Remember the pKa is 16, 4/3 of 16 is 21, so 21 kilocalories per mole. So that makes it 21 kilocalories easier to make the anion because you're not making proton, you're making water. Okay, so that's going to lower these. Is that going to do the trick to be able to isomerize? Well, now the half-time would be about 30 years at room temperature, okay? But if you warmed it to 150 K, it would be about 2 minutes. So if you heat it up, you could make the isomerization occur. And then no matter which of these you start with, it's going to equilibrate, and this is the lowest energy form, and that's going to be everything except there's going to be 0.1% here and 0.03% there, okay? So no matter which of these you start with, you're going to get that. However, suppose you use a really strong base, like amide. So now that favors loss of a proton, that is, it'll take the proton, by 45 kilocalories per mole. So now we're going to lower those ions even further, like that. And notice what happens on the far right. It goes all the way down there. And that's now the lowest energy form, if you have NH2 minus. So instead of having it be all here, which is what you're going to have in any equilibrium among the neutral forms, right? This is going to be the lowest energy form, right? So everything will be over there, 7.2 kilocalories down, which means that at equilibrium you're going to have only 0.0001% of this stuff, which was always the favored stuff before. So everything is now over here. So the trick is now you neutralize it very rapidly, right? So the trick to obtain a terminal acetylene, remember that anion is the one that has the anion on the last carbon. That's why it's such a stable anion, because it's sp hybridized. So you equilibrate with an amide base in an amine solvent to form the terminal anion. Then you quench it by adding water to donate a proton to the terminal anion and also to the RNH. So you have only hydroxide now, which is too weak to allow equilibration. Or if you want to, you could just add acid so that you don't even have OH there, although that's gilding the lily. You've already made it by not having that really strong base. So you stop the equilibrium, you would put the proton on the terminal acetylene, so you can go from the internal, the more stable one usually, to the terminal acetylene using this trick. Okay, so that's all I wanted to say about acetylenes. And now we're going on for the next, these 2 lectures, and a little bit probably still beyond the exam, to talk about conjugation and aromaticity. So conjugated pi systems is what you're talking about. The name conjugated comes from an interesting root. Conjugated systems are when you have pi bonds separated by a single bond. And they're called conjugated because they're yoked together. The word yoke is the same root. It's yoke comes from jungere, from jugum, which is to join, right? So they're joined together. They don't act independently. We talked about this already in the first exam when you memorized functional groups. And on the exam, I had a thing that had both a carbonyl and an amine, and they were near one another, but it's not a carbonyl group and an amine group. It's an amide group. They're conjugated and they behave in their own special way. So now we're going to talk about conjugation. So conjugation is where the localized orbital picture, which remember we've talked so much about pairwise 2 atoms coming together to give a bond and an antibond or isolated atomic orbitals. That was our intermediate between hydrogen-like atomic orbitals, which we really understood. We had a table that we could draw them out. And the computer MOs, which look very complicated. But in between were these pairwise things, right? But sometimes we have to think more deeply when these things are conjugated. They don't behave that way, okay? So when does conjugation make a difference? So first we're going to look at experimental evidence, and then we're going to go into the theory. So a classic example is allylic stabilization. Allyl comes from the word the same as aioli, or L in French, meaning garlic. There's a sulfide in garlic that has a double bond, then a carbon, double bond, single bond, and then a functional group, a sulfide. So that's an allylic sulfide. It came from garlic, right? So allyl is these 3 carbons in a row, double bond, single bond. So you can get special stabilization when you have functional groups involved, when you have intermediates involved there, like the cation intermediate. So the energy for pulling off a chloride for primary and secondary are these values in the gas phase. Of course, very hard to separate the ions. But if it's allylic, it's as good as being secondary, right? So allylic is very good, right? Or if you look at anions, look at the pKa of the OH. Here it's 16, we know. If you have a double bond here, it falls by 6 orders of magnitude, right? And in the case where it's an oxygen here, it falls by another 5 orders of magnitude, and you actually call it an acid. Okay, so the anions get much more stable when they're allylic, by about 8 kilocalories per mole in the case of the enol. Okay, or free radicals. If you look at the bond dissociation energy of a normal CH bond, 101, but if you make a double bond next door so that this is allylic, it's 89. It's stabilized by about 13 kilocalories per mole. So there's stabilization of these reactive intermediates when they're allylic. Okay. Now let's look at some more detail about some of these, like the cation intermediate. The addition of HX to butadiene. We talked about HX, halogen acids, adding to single double bonds. How about adding to 2 double bonds? Okay, so at minus 78 degrees, you can add HBr to butadiene, and you could imagine the H plus going on one of the internal carbons to generate that cation, or it could go on the terminal carbon, the other regiochemistry, and generate that cation. Which of those do you think is more likely to get? Which one would you prefer if you were the proton? Aisha?
The one that's down.
The lower one. Why?
It's a secondary cation.
First, it's secondary, and it's also allylic. right? Which the first one isn't, because from this carbon to the double bond, there's an intervening saturated carbon, right? It's not two double bonds or two sets of p orbitals separated by a single bond. There's no overlap between this p orbital and that p orbital. Okay, so the second one is of course also that, because those are resonance structures. But as Aisha tells us, the top one doesn't look so good. So we're going to get one of those. But then in a second step, we add bromide, right? If we do that at minus 78 degrees, of course we generated the bromide when we attacked the proton. So we could imagine getting those two forms by attacking this intermediate, which is denoted by two resonance structures. Now, in fact, you get those in the ratio 80% to 20%. Does that surprise you? What would you expect for the ratio of these two? Here you have a terminal double bond. Here you have an internal double bond. Which one is more stable? Do you like to have double bonds more substituted or less substituted? Arvid, do you remember? More substituted. So this is backwards, right? It's 4 to 1 in the wrong direction. Now, that means that if you allow it to equilibrate, it'll go the way Arvind wants it to, right? But the initial product formed at really low temperature, at dry ice temperature, is backwards, okay? You can cause, this in fact can ionize to go back to the cation and then come back, and that's a route for equilibration between these two. And you can encourage the bromide to come off by putting ferric bromide in. If you want to, it'll go faster. But at any rate, that's the equilibrium. So this is called kinetic versus thermodynamic control. So thermodynamic is equilibrium, but kinetic is what you get first. And those aren't necessarily the same. It's this case we've seen before, where you start and you go up a certain rate and then down to a product, or you could go to a more stable product. Hammond would say you'd go faster to the more stable product, but sometimes, remember, it crosses, and it's easier to get to the less stable product, and that's example here. It's a kinetic controlled at low temperature. Now, why? Why, when it's a question of rate, the first one to be formed, why do you think you form the top one? Anybody got a theory? Yeah.
The positive charge.
What about the positive charge?
The electrons on the bromide ion are attracted to the positive.
Right. It looks like this is a secondary versus primary. More of this, so that's where it attacks. That looks like a good explanation, and that's what you'll see in almost all textbooks. So very good, Anurag. You can write a textbook. Okay. Let's look at the orbitals that are involved in this just for fun quickly. Okay, so here's a top view down on the 4 p orbitals of the butadiene, and here's the side view, right? So here's the HOMO minus 1. That's the favorable combination of those 4 p orbitals, okay? And here's the HOMO. That's the unfavorable combination. It's pi on this side, but unfavorable between them. Okay, that's the HOMO. The LUMO has 2 nodes among the 4 p orbitals. And what do you think the LUMO plus 1 looks like? It's got 3 nodes. So you got no nodes, 1 node, 2 nodes, 3 nodes, okay, for combinations among those p orbitals. Now, the HOMO is the one you want to attack with the proton, okay? So where should you attack it? Probably you get the best overlap around in there, right? Or you could look at how the potential on the surface that we've talked about to see where the best place for a proton is, and it's in the orange region. So that seems to more or less agree. It's about there. So that's where the proton should attack, at the terminal carbon. And then it would give the propenyl cation, right, which is shown here. There are 3 hydrogens on this carbon here. Okay, so that's the best product then. Okay, now that's the HOMO minus 4. It's a little bit silly to look at that, but it's actually a CH bond that's hyperconjugated a little bit with the p. Now we have 3 p orbitals, here, here, here. the one that was here became part of this CH bond. Okay, now how about the rest of them? Okay, here's the HOMO, it's pi. Here's the LUMO, 1 node. And here's the LUMO plus 1, 2 nodes among those 3 p orbitals. Okay, so that's the propenyl cation. There's the LUMO that you're going to want to attack if you're the bromide, right? So you could attack at either end, not at the middle, okay? And if you look at the surface potential, the worst place for a proton is where it's very blue here. So that would be the best place for bromide to come, but it's in the plane of the ring. It's not a place you can form a bond, okay? Okay. If you want to come in from the top where you can form a new bond, it's a little bit green there and a little bit blue, even better there. So the blue place, plus 144, would be the best place to attack if you want to form a bond. That's where bromide would tend to be in order to attack. So one would think that this is exactly what Anurag has proposed, right? That it should attack there. But here's a really interesting paper that was published in 1979, where what's being added to is not butadiene, but pentadiene, another methyl group on there. So they add DCl, which adds to the end to get the, as one would expect, to get the more substituted allylic cation, right? But now there's something interesting about that. That's symmetrical, except for the fact that there's a deuterium there, right? So if a bromide now comes in, or in this case they use chloride, it could attack either here or here, right? If it attacks here, you get the 1,2 addition, D and Cl. If it attacks here, you get 1,4 addition, D and Cl, okay? Now, if it had to do with the kind of thing we talked about before, where's the best place to put a chloride, where do you get the best overlap, and so on, that's the same here and here, right? So it should be 50-50 in this case because of the intermediate being symmetrical. When it was butadiene, we didn't have this methyl group and it was unsymmetrical, and we did the analysis of the previous slide, where would be the best place to attack. But now it's symmetrical, so we should get 50-50. So here's the product distribution done at a bunch of different solvents at different temperatures. And just look at a couple of these. If you do it at room temperature at 25 degrees, you get half again as much of this as you do of this. More chloride adds here than here. And if you do it at low temperature, you get 3 times as much addition here as here, even though it's symmetrical. So we've got to find some other reason why, when we do this, the chloride tends to attack here rather than here. 1,2 addition rather than 1,4 addition. Can anybody guess a reason for that? Well, let's look at the mechanism. The first thing that happens is we put a proton on and generate this cation and also chloride. Now do you have an idea? Aisha?
It's closer.
It's closer. It has to move farther to get to 1,4 because this backside attack on the hydrogen meant that the chloride has to be out here someplace, closer to this end than to this end, right? So it appears that rapid collapse of this ion pair that you make, before ions can move independently and establish true symmetry, that competes, so that the collapse competes with the motion that would make it truly symmetric. So it looks like it might not have anything to do with where the charge is on the surface or which resonance structure is better, right? It's just where the chloride got formed, and it attacks really quickly when the ion pair collapses. So you could have written a textbook, but you might not have been right. Okay, now, allylic transition states also are unusually stable, and we actually mentioned this before, but if you look at an SN1 reaction, so you're breaking away to get a cation, the relative rates are If you take 100 for T-butyl, which is very easy to form the T-butyl cation, the secondary is 10 to the fourth times slower, and the primary just doesn't happen. It's way slower than that. Okay? But if it's allylic, then it's five times faster than secondary, even though you might think it would be primary, right? And if it's allylic with a methyl group on it to make the cation more stable that you're forming when you break off chloride, it's half as fast as a tertiary T-butyl chloride. If you put two methyl groups there, it's very much faster, 63 times faster than T-butyl, right? And if you put a methyl group here, however, on this carbon, so we put a methyl group here, it accelerates enormously. If we put two methyl groups there, it really accelerates. If we put a methyl group here, however, on the other end of down here in the middle. No, wait a second. No, I'm ahead of my game here, sorry. If we put it on the other end, it's just as good, okay? But this is what I wanted to tell you. If you put the methyl group in the middle, it doesn't help at all. So the methyl group has to be on one end or the other of the cation you're going to make when you lose the chloride, right? In order to get that acceleration. If you put it in the middle, it doesn't help. So again, we could look at where the charge is in the cation, and you have to put for the methyl to be effective in accelerating it, in accelerating the SN2 reaction, SN1 reaction, it has to be where the charge is going to be. Okay? Now, how about SN2? Okay, if we take the rate of ethyl chloride to be 1, reacting with ethoxide, it's 37 times faster if it's allylic, and 97 times faster if you put a methyl on, and 560 times faster if you put two methyls on, right? If you put the methyl in the middle, it doesn't help compared to not having the methyl. But if you put the methyl at this end, remember before when we were doing SN1, forming the cation, we could put it either at this end or this end and got the same rate. Now it's slower here. Any idea why it should be slower in this case for the SN2? How about the rate of T-butyl for SN2? If you have T-butyl, 3 methyls, and you want to do SN2, it's very hindered, right? So this hinders the approach because remember you're making a pentavalent carbon in the transition state. So allylic helps, but this time you can get help from the methyl at this end, but not at this end. Okay, now so we looked at the allylic cation, we looked at the transition states involved in forming the cation and in the SN2 process. Now let's look at the allylic anion, and that's easily done by looking at the acidity. So we have a pK of something like 52. It's hard to measure for that, but if you have its allylic, it's 43, right? And that's helped by 9 powers of 10, or about 11 kilocalories per mole of stabilization for losing that proton at equilibrium. And if you have a phenyl ring there, it's benzylic. And now it's even more so, about 16 kilocalories per mole. So again, having these pi things where they can overlap with the anion that's being formed is very favorable, the order of 10 or 15 kilocalories per mole. Okay. How about free radicals? Well, here's a very interesting, these figures came out of this paper by Ziegler. This Ziegler is not the Ziegler who teaches Chem 220. This is the one who invented Ziegler-Natta polymerization and became quite wealthy. Okay, so in 1942, working in Germany in the Second World War, he was studying this process. He could get a 58% yield of substitution. This bromination is a substitution, pulling off one of these hydrogens and replacing it by bromide. Okay. Now, for this purpose, the paper that describes this particular compound, which is called N-bromosuccinimide, right? And in ether solvent in 30 minutes using light. What does the fact that he was using light suggest? That it might be a free radical chain reaction, right? He was able to get this 58% yield. Now, where does he get the N-bromosuccinimide? So that compound is succinimide. Okay. He reacted it with base to make the anion. Does it surprise you that that anion can be formed with hydroxide? Remember, NH has a pKa of 30 or something like that. And hydroxide is only 16 at the pKa of water. How is it able to pull off that proton? What's good about that anion that we formed? Megan, do you have any idea?
The lone pair is stabilized by the pi star orbitals on the
Right, you have two carbonyl pi stars to stabilize the high energy electrons on this nitrogen. Okay, so you can make that anion, but it can, the pKa incidentally, that is 9.5. It's a very strong acid as NH bonds go. And that could do an SN2 reaction on Br2 to put bromine on the nitrogen and make the bromide anion together with the sodium ion that came from hydroxide. So that's how we got NBS. But you can take it apart again if you, instead of using base, use acid. So if you use HBr, you can protonate this. You can protonate that oxygen, and then you can draw a resonance structure here, like that. So it's easy to protonate here. But now you can take the bromide and do an SN2 reaction on the Br, right? So you generate this, now neutral, right? Which is an enol that easily isomerizes back to the starting material. So in base, you can make this with bromine. And if you add HBr, you come back, right? And of course, also get Br2. That was what was formed here. So you can get the Br2 back again if you want to from NBS. Now, back to the reaction. We can imagine doing a reaction of Br2 with a double bond. What reaction have we talked about, Br2 plus a double bond? It's the addition, electrophilic addition to a double bond, right? We talked about this a good deal. No doubt it will be covered on the exam next Monday. Okay, you do this here at room temperature in the dark. You get the bromonium ion first. Remember how we talked about that? And then you get anti-addition. Okay. Now, but suppose you want to do substitution. That's what Ziegler did, right? He didn't add bromine to the double bond. He replaced an allylic hydrogen with bromine. So those substitutions are typically free radical substitutions. So you could have this same compound, but I show the hydrogens, because if you have ways to get a free radical, like a bromine atom, it can pull off, get HBr. And this, but remember we use bromine here, not chlorine, because it's slow and selective. So if you use chlorine, it takes not only this hydrogen, but also this hydrogen almost as rapidly. It's not selective, but bromine is selective. It's uphill. Okay, then you can react it with Br2 and replace where the hydrogen is with bromine. So you've done allylic bromination. And of course, this allylic intermediate was resonant in this form. You could put the bromine either here or here. So you also get that, which is the same material in the case shown. But if you had a substituent, it would be in a different position. If you had something on the ring substituted here, it would be a different compound. Okay, and it also gives a bromine atom. Why is that relevant? What happens to the bromine atom? Matt?
It gets reused in the free radical chain.
Goes back to the start. It's a chain reaction. Okay, so how do you control which you're going to get? Are you going to get bromine addition or allylic substitution? Right? Can you think of any way of controlling which of these, you put bromine in, which of these things is going to operate? Is there a way, any handle you have on it, Matt?
You can use photo initiation to get the radical.
If you use, notice this one's done in the dark, right? If we can't get the radical, we won't do this one. Okay, so one idea is to keep it in the dark, right? Don't use the initiator, okay? Now, suppose we want, so that'll allow us to do this one, that dark one. How do we get this one to happen? Well, you might say we use light or use an initiator, right? But this can still happen if you have the light on. You can still get that, right? It doesn't require dark, it's just this one requires light. Okay, so this one would also be going on. But there's another way, which is to minimize the concentration of Br2. Now, why does that have anything to do with it? This is a really interesting thing about the kinetics of the top reaction, right? It's second order in Br2. That looks really weird. Why do you need 2 molecules of bromine in order to do this? The reason is that you want to make, when you get the Br plus coming on, Br minus is coming off from Br2. So you have to get Br minus. And in fact, Br minus is stabilized by reacting with Br2 to give Br3 minus. So in fact, what happens is that the second Br2 helps the bromide leave from Br plus in a nonpolar solvent like this, right? So it's second order. So that means if you have a really low concentration of Br2, this one gets really slow because it's a bad leaving group, right? It's like making the Br minus leave by putting Br2 in is like making OH leave by putting a proton on it, make it a better leaving group. Okay, so we want to, if we minimize the concentration of Br2, we'll slow this one down, but that reaction with Br2 is very fast. Remember, the first step of this is endothermic, is slow, but that step is really fast. Okay? So we can tolerate a low concentration of Br for this purpose, but how are you going to do it? Right? Because suppose you put in just a teeny amount, you have just a teeny amount of Br2 there. Okay, this starts in, but quickly you've exhausted the Br2, and now the radical chain stops, right? And that's the end of the line, right? Now you could say, I'll very carefully run in Br2 very slowly, right? Just to balance out. But when you put a drop in, the bromine concentration is higher in that drop locally, right? So you're going to get this reaction because of the local high concentration of Br2, right? But this is where Ziegler comes in with his clever NBS molecule. This looks like it's tedious to impossible to maintain a really low concentration of Br2 while it's being consumed all the time. But notice that this reaction also yielded HBr, right? Whenever that happens. And if we have N-bromosuccinimide plus HBr, that's the reaction we looked at on the previous slide that destroys N-bromosuccinimide. Takes it back to succinimide. And remember what the other product was? Br2. So isn't this neat? Whenever a Br2 molecule gets used up, a new Br2 molecule is created by this reaction, right? So it automatically maintains the minimum possible concentration of Br2. Every time you use it, you get a new one. You don't have to sit there with your burette trying to run it in very slowly. So that's the trick with N-bromosuccinimide. Now, so we've looked here at a lot of different allylic stabilizations, right? But dienes can also be conjugated. And how much is that worth? Okay, we can look at the heat of combustion of this one where they're not conjugated and this one where they're across a single bond, these isomers of one another. And you can see that the conjugation seems to be worth about 7 kilocalories per mole. Or down here, it seems to be worth about 8 kilocalories per mole. But these numbers, although they're claimed to be very precise, are big numbers, right? And that, I think that precision might be a little bit overstated, right? If you look at the heat of hydrogenation, the heat that's given off when you add H2, then you can see that these are all 30. I'm going to let you go after you make 2 guesses, okay? Now, guess what it should, this double bond, this double bond, this double bond, they all give off 30 kilocalories per mole of heat. How much should this one give off when you hydrogenate both double bonds?
60.
Lean? How about this one? 60. Natalie? 60. How about this one?
Something bigger. Much more. Oh, less.
So conjugation, this one is more stable. It doesn't give off as much heat, right? And it seems to be stable by about 4 kilocalories per mole. Okay, now you can go.